It would say, right?
Okay. All right.
Hi, everyone. My name is Sharad, and I am I'm Dr. Shen's current master student. I would be graduating in a couple of weeks, and Dr. Shen wanted me to cover this one small lecture on practical applications of topology optimization. So far, Dr. Shen must have covered various optimization techniques that can be applied on various structures, ranging from gradient-based to evolution, and quite recently topology optimization. Today I would be talking about topology optimization and how that readily applied code called 99-line code can be used to compute various structures for various boundary conditions. So yeah, let's get started. So far, Dr. Shen must have covered what is the flow of topology optimization. We start off by initializing, randomly guessing some values of the design parameters. And the design parameters or design variables are nothing but the density values of the design domain, also X in our case. Once we have the initialization, we perform a finite element analysis. We compute the displacements, and according to the displacements, we compute the compliance of the structure. And the compliance for our case is the objective function. So we compute the objective function rather, and then we compute these. Then we perform the sensitivity analysis to compute which design parameters or densities in our case are influencing the objective function more, so that we can get rid of the lesser influence. Then once we compute once we perform the analysis, then we go on to filter the whole design domain based on the sensitivities. Now this is done to get rid of some of the limitations of the topology optimization code, and I will be talking about filtering in the next 10 minutes or so. Once we filter, we update the design variables using an optimization criteria. Here we use optimality criteria, but instead of optimality criteria, it could be anything from evolutionary to gradient based or anything. Optimality criteria is rather gradient based itself. So once we update the design variables, we check whether the update or the delta of X or the change in the density values are within the tolerances or not. If they are, we end up with a final result. If they are not, we go back, run the finite element analysis, and so on and so forth. So that's like the rough flow of topology optimization, irrespective of code that you would use. But yeah, this is like a standard process of topology optimization. Next. So in MATLAB, the code that we are using is called a 99-line code, primarily because the code consists of 99 lines of code. So the function call looks something like this, that the function called top consists of 5 parameters. The 5 parameters being n, elx, n, number of elements in x, number of elements in y, volume fraction being the initial density guess that we assume that the structure would be having, and this volume fraction is maintained throughout the structure. So if you assume that of all the design domain, 50% of my domain should have material, then we would take this value to be 0.5, and even after the end of the optimization iteration, we would end up having the volume fraction as 0.5. So in optimization terms, this is nothing but a equality constraint. The other two parameters are penalty factor or penalization factor. Now this is something Dr. Shen must have covered previously about the theory where this penalization factor comes in, and the reason why we have a penalization factor is to prevent the intermediate densities, which is something we do in the formulation called SIM, which, by the way, we are using. And the last one is the radius, the minimum radius of the filter. This is something I will be talking about in few minutes, but this is nothing but a radius of the circle under which all the densities would be smoothened. So this ensures that we don't end up in a checkerboard kind of a pattern and all the densities are smooth, because if you work on the 1999 code, you will see that sometimes you end up having densities somewhere in the middle, and that in design does not really happen because you don't have material hanging in places. So that's why we need radius of the smoothing filter. Next. So yeah, now we know about the arguments of the function. We have 5 arguments. Let's get started with the code itself. So the code looks something like this, and this is the exact code that that will be given to you, called top.m, .m being the MATLAB extension. And we start off, now go back and think about the chart that we were talking about. We start off by initializing, and we initialize the design parameters, right? We initialize the design parameters, could you go back? We initialize the design parameters with the volume fraction constraint that we had given previously. So assume that you have a square and you have a initial volume fraction value of 0.5. That would mean that all the pixels in that square would have a value of 0.5. So it's a uniform distribution for the time. Now what happens is that once we run all the iterations, these density values would change, but again the final volume fraction of the whole domain would be constant 0.5. Next we start off with our iteration loop, and the first thing we do here is the finite element analysis. Now in the finite element analysis, could you go to the finite element analysis block? If you, yeah, it's on the next page. It's right over here. Yeah, so you go to the function of finite element analysis, a function named FE, and here basically for finite element analysis you are basically trying to solve an equation of equilibrium, right, which is force is equal to stiffness times displacement. First we know about the stiffness, and we also know about the forces, because we know the applied force, and we also know some information about the boundary conditions, which would come up in the displacement matrix, which I'll be talking about in a bit. So first we have an element matrix here, and this element matrix depends on what kind of finite element you choose particularly, and this is something which has been hard coded for this code. And if you scroll down, we also have a hard code for this. Remember, this is LK. If you scroll down, this is what we go to for computing our element stiffness matrix, and for each element this is our stiffness matrix. Now can you go back to the same thing? Yeah, so we have the element stiffness matrix. Once we have the element stiffness matrix, we initialize the global stiffness matrix and the force matrix. These are, one key point to note here is that the size of the global stiffness matrix is the number of elements times 2, which I will be talking about why it's times 2. Moreover, the more important thing here is that the size of the force matrix is the number of elements, comma 1. And the reason it's 1 is because it's a row matrix. it consists of rows and only one column. Now we have the local stiffness matrix or elemental stiffness matrix. We want to compute a global stiffness matrix, and this is where we compute the global stiffness matrix. We run for each element, we compute the stiffness matrix, and then we add the product of the element stiffness matrix times the density value, and then we penalize that further. Now this is something which is in the theory and which was covered in the last lecture. Now we have the global stiffness matrix ready with us. Now we want a force matrix and a displacement matrix, right? For force matrix, we already have initialized the force matrix, which is can you pan like over here? I can edit this conversation out. Okay, so the force matrix is so the force matrix is something like this. It consists of 2 cross n cross m or 2 cross total nodes in x, total nodes in y, comma 1. So it has one column. Now the reason why we have a 2 here is because if we have an element like this, we have 4 nodes, but each node has 2 degrees of freedom. So each node has 2 degrees of freedom. So we have in fact 8 degrees of freedom. And the stiffness matrix and the force matrix is defined by the degrees of freedom, not by the elements or the number of nodes. So that's why we have 2 times in the global stiffness matrix and 2 here in the force matrix. So we have our force matrix already defined. We already have our global stiffness matrix. Now we want to define the loading force that we apply. And for this case, we apply the force at first node, but second degree of freedom. So first degree of freedom would be in the x direction. The second degree of freedom would be in the y direction. So what this means is that if we have something like this, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 nodes, which means 18 degrees of freedom. The force that we apply here is on the first node, but in the y direction. So it's something like this. And the reason why it's in the downward direction is because our value is equal to -1, negative of 1. So negative is lower direction and positive is upper direction. So we have a force over here. Now our force matrix is also complete. The next thing we want is a displacement matrix. So the displacement matrix consists of known displacements and unknown displacements, right? So we first segregate the known displacements, which are nothing but the boundary conditions. Here we have boundary conditions of fixed nature, meaning they are fixed. Some boundary conditions, the displacement would be 0, and if you see here, the fixed degrees of freedom is starting from first node, which means the displacement is 0 in the x direction, till till the number of elements in y, or till the end of first column, and the spacing between them is 2 degrees of freedom, which means that the boundary condition here starts from, for the first node, what we do is we constrain the x degree of freedom, so which is something like this, only the x degree of freedom, and we do so for the whole first column. Now why did I assume that this is the whole first column? Is because the number of elements here are 2 in y direction, and if you apply 2 here, what you get is 6. So the fixed boundary condition here start from 1, 2 is free, 3 is again a boundary condition, 4 is free, 5 is again a boundary condition. So in other words, what we are trying to do, we are trying to constrain the left edge of our boundary as constrained in x. So the displacement in x is 0 for this edge. The next fixed boundary condition here is the last element. So if you evaluate, this is nothing but the last element. So we are also trying to constrain the last element and the last boundary condition in y. So we constrain the last node and the last degree of freedom in y. So we have degree of freedom, we have a constraint in x, we have a constraint in y, we have a loading force. So that makes our finite element model complete, and now we can compute the analysis, which is done by line number 85. We were here right now. We computed the fixed degrees of freedom, and these are all degrees of freedom possible, which are nothing but starting from 1 to the end of all the degrees of freedom. And then we segregate these using a function called set diff, which is nothing but it differs degrees of freedom which are not fixed, and we call these free degrees of freedom. And then we compute a standard finite element equation. We compute the degrees of freedom for the free, we compute the displacements for the free degrees of freedom using k over f. And once we have that, we take this u, this whole complete u as the result, and if we look here, we end up over here. Now we have done the finite element analysis, we have the displacements, and the next thing what we would be doing is computing our objective function and the sensitivities. To compute the objective function, the requirement is you should either know a heuristic, an equation how to compute the objective function, or some mapping function. Anyways, we know the equation to compute the sensitivity when we have the displacements, and for each element we compute the sensitivities as well as the compliance. So compliance is our objective, and the sensitivity is something that we would process further. So this is where we complete the second part as well in the iterative loop. Now the third part is the filtering of the sensitivities. Now if you remember, we perform a filtering action because we want to smoothen the design domain. We don't want abrupt material and then no material boundaries in the design domain. So a good way to perform this kind of a thing is to perform something called a weighted average, or in image processing this is also something called as applying a Gaussian filter or some imaging filter. Here if you go to the function call, oh yeah, it was right there. Here. Yeah, so this is a filter, and what we are trying to do is nothing but a mathematical implementation of a formula which was discussed in the last class, and that has been implemented over here, these three parts. Now it's relatively a little bit difficult to explain how it's implemented because it's rather straightforward, and we don't have the means right now to explain the formally how we perform, how we compute. It's nothing but a weighted average on the numerator as well as the denominator to normalize. Very extremely trivial stuff. Can you go back? So here, after we are done, we end up with the sensitivities that do matter, and the sensitivities of each of the densities. Once we have these sensitivities, we go to the last point, which was the process of updating the design variables. And how do we update? We perform a optimization method, which could be optimality criteria, which is a gradient-based method, or it could be any other method, be it evolutionary, genetic, or even machine learning that we as a research group work on. So if you could go to this function. So the concept of how optimality criteria is derived is very trivial. We have an objective function, we compute the gradient, the constraints are added to the objective function using a Lagrangian method, and then we take the gradient, we compute that Lagrangian parameter, and then we go on and on until the change in the Lagrangian parameter is until the change in the we compute the Lagrangian parameter using some algorithms that could be golden section, which Dr. Shen covers in his lecture, or could be bisection algorithm. And then how bisection of gradient or golden section work is we go on and on, we compute the parameters, and then we check the tolerances, whether they lie within, whether the bounds, upper bound and the lower bound, lie within a particular value. And that's exactly what is done over there. We start off with two bounds, one being 0, the other being extremely large, and we move by a value of 0.2. And if you checked line number 43, this is where the optimality criteria has been defined in the code. Now this is something that is covered by Dr. Shen in the last lecture, and this is nothing, this looks a little different of how it is defined in theory, but this is exactly the same. In theory, there are 3 if conditions, that if our certain parameter lies less than a certain parameter, we have this formally. If not, we have this formally. If this lies somewhere else, we have another formally. So all of that, all 3 if statements are achieved here using min and max conditions. So once we have the optimality criteria done, we compute the new x density values, or the new material density of each of the pixel, and this is exactly something that we want. So could you scroll back? So right now we are here, line 29. Line 29, we we update our design using the optimality criteria method. We compute the new density values. And then this process goes on and so forth. So we print the results. This is something done such that the designer keeps an eye on what is happening. We print, we plot the densities, and then this end goes all the way to the, this goes all the way to the while loop that we have over here. Yeah. And we check whether the change of x versus the x old that we had, whether the, so this change is nothing but the change in the density values of the previous iteration versus the density values of the new iteration. If they lie within a certain value, we end the whole process and we come up with a final optimized or suboptimal or optimal, that's something we can debate on, but we come up with an optimal structure, which is exactly what we need, right? And that's it. That is exactly what the basic code of topology optimization does. And this code is extremely straightforward, and most of it, well, this code is actually based on a paper called 99-line implementation in MATLAB, which Dr. Shen would be sharing the link, or he would share the paper itself with the class. All the explanation about this code has been given in detail by the same author who created this code, and that's everything that I have to share about the application of topology optimization to mechanical design. So thank you for the time.